Hello, it's your grumpy old middle school science teacher again, old Doc Palmer. Last week we talked about atoms, and I want to go into a little more detail to help you understand what atoms are. Because all of chemistry is based on the atomic theory of matter and the fact that we think that all matter is made up of these little bitty tiny particles that we call atoms. Now, I said last week that all atoms are made up of protons, electrons, and then all but one atom also has neutrons. The protons and the electrons exist in the nucleus of the atom, and we call those two particles nucleons. The electron is a whole different kind of particle, if we can call it a particle, and we'll talk more about that in the future. The ancient Greeks, 2,000 years ago, thought that if you broke something apart, you could keep breaking it apart until finally you would get to a piece that was so small it could no longer be broken apart. And we don't really have documentation of what they thought those little parts looked like. But I can imagine that they thought it looked like, if I started with a rock, then I'd have a tiny little piece of rock that I could no longer break. And that would be the fundamental particle. And that's where the word atom comes from. It roughly means unbreakable, indivisible. It can't be taken apart. Modern science really started about 300 years ago, and as we develop better understanding of things that were going on, the theory, the concept that all matter is made up of little particles that are unbreakable began to bubble to the front. And there was some strong evidence to support that. Things like when you broke materials down into their component parts, like if you take water and you run electricity through it, which they started doing, 250 years ago, then they noticed that if you ran electricity through water, bubbles would start forming on the two electrodes that you were using to run the electricity through the water. And if you captured those bubbles, they always came out in a ratio of 2-to-1. One electrode would have twice as much gas come off as the other. And there were some other experiments they did where they broke things apart, and they began to think that there was some kind of relationship in the nature of matter that meant there must be particles that were of the same size. One of the things they did is they began to look at different masses of material, of identical materials, and began to realize that there was some small number that you could divide into the mass of just about any of the same materials. And they began to think that maybe that little tiny number was the mass of a single piece, the smallest piece. In other words, two materials could only differ by whole numbers of those little pieces. I used to do a lab with my students where I would take paper clips and I would put them in plastic film canisters. Now, a lot of you don't know what film canisters are, but before there were digital cameras, we had to go to the store, we had to buy film, and we took that film, and it was in a little plastic canister, and you took it out of the canister, and you put it in your camera, and you closed the back, and you rolled it, and took pictures, and you had to crank it, and when you finished, you rolled it back up into the little can, you put it back in a film canister, you took it to a photo lab. Later, towards the end, it was mostly pharmacies would do it, Walmart would do it. You'd take that film, and you could keep the canister, or you could go by and you could pick up the canisters. They were little bitty plastic things about this big. If you've never seen one, someday I'll bring one out. But I had a set of these that were labeled A, B, C, and D for every lab group, and in each of the canisters, there were a different number of identical paper clips. And what we did in lab was the students had to determine the mass of each of the canisters and then compare their differences in mass. And the steps of the lab, they eventually realized that there had to be something in the canister that had a specific mass, and that each canister had different numbers of those things, and they could figure out what the mass of that thing was. They weren't allowed to open the canisters. It was a black box. Scientists began to do similar experiments in the 1800s. And the first experiments with radiation, we began to take glass tubes, put vacuums on them, they put electrodes in each end, and they discovered that there was something flying between the electrodes in this vacuum, and if they put certain things on the end of the tube, it would light up when they energized those electrodes. And so they began to think there was some little particle that could be moved by electricity. And they began to theorize that there were different particles making up these little things called atoms. And over lots of experimentation, they began to realize that there was a big particle, and there was a tiny particle, and they initially called the big particle protons and little particle an electron. And the early theory of the atom was that these just kind of existed in what is known as the bread pudding model. Imagine you have a loaf of bread, or bread pudding if you know what that is, and it's got raisins in it. And the raisins would be the protons, and the bread pudding would be all the electrons that are around there. And then some experiments were done where they took and they fired electrically charged particles. They weren't sure what they were at the time. Turns out they were protons. At a piece of gold foil, very thin, very dense foil. And had it been the bread pudding model, had that been what was really going on, they would have expected that these particles, as they went through this pudding of negatively charged electrons, these positively charged particles would have been spread out and dispersed. And what happened was most of the particles went straight through. They weren't deflected at all. Some were deflected at certain angles. Some were even deflected back at the device that emitted them. And in analyzing the data from that experiment, it's called the Rutherford gold foil experiment if you want to look it up. A piece of gold foil so thin that if you touched it, it would probably break. They began to realize that maybe atoms had lots of empty space, and that there were some very massive particles in the center of the atoms that if the particles they shot at this gold foil bounced back, they hit one of those and they bounced straight back. And since these were positively charged particles, whatever they hit had to be positively charged. But that most of the space in that material was empty, and these positively charged particles just flew right through. Some of them were close enough they got deflected off to the side. From those experiments, they came up with a model of positively charged nucleus made up of protons with electrons going around them. And you've probably seen that drawing because it became kind of a meme, if you want to, for atoms and atomic and nature. And the idea was that these electrons orbited around the nucleus much like planets orbit around the sun. Well, turns out that wasn't quite right. But just like so many things that progress in science, we develop a model, you also can call it a hypothesis, that makes predictions, and then we can test those predictions to see if our model is correct, and that gives us more insight to then modify our model. And so starting with this orbital electrons going around the nucleus, we made some predictions. One of the predictions was that, well, since protons are positively charged and electrons are negatively charged, and the protons would be pulling the electrons toward the center, if the electrons were going around like planets going around the sun, they would be pulled towards the center of the nucleus, and the only way they could stay in those orbits would be to constantly take in energy, and that wasn't happening. So the model had to change. And the model we have today, and I'm not going to go into a lot of depth on it at this point, we'll talk a little bit about it later, is that the electrons exist in what we call orbitals. Thought they were in orbits. They're not in orbits. We call them orbitals that surround the nucleus, and that they are kind of more like a cloud. In fact, we call it the electron cloud. If you're talking about all the electrons around a nucleus, we call that the electron cloud, and each electron is in an orbital, and if there's two electrons, they can share an orbital. They have a quantity that we refer to as up and down. Don't let that confuse you, because it's not really what you think of as up and down. But any orbital can have two electrons, one with what we call up spin and one with down spin, and they're stable in that configurations. And we will look at some orbitals in future videos, because understanding the orbitals that electrons are in is kind of the basis of how all chemistry works. And so we're going to talk about that. After some more experimentation, they began to realize that there was something in that nucleus other than a proton. And in every element on the periodic table, every element that we know of in the universe, there are protons in the nucleus and there are neutrons. There's one exception, and that one exception is hydrogen. And hydrogen is kind of a weird, different kind of thing. And we're going to talk about what makes hydrogen very different than all of the other electrons. Now, in this video, I'm going to be using a website called P-Table. And I have permission. I will put the link down below. The person who developed P-Table has given me permission to use it in my videos very kindly, and I will put his name and a link to him and his work. But P-Table is a very powerful tool for looking at atoms. And you'll notice that P-Table right here is color-coded, and you'll notice that as I scroll over things, colors changes to tell us things about them. And hydrogen is this first square up here on the periodic table, and it's colored green. And if you look way over here, there's some green elements as well. And when you scroll over here, nonmetals, hydrogen turns green as a nonmetal. Again, there's some controversy about that. Hydrogen's weird. Hydrogen can sometimes act like a metal, sometimes acts like nonmetal. Again, we'll talk about that. If you look at just about any periodic table that comes up, hydrogen is over here on the left-hand side, very top, and it's usually separated from those elements below it. When we talk about the periodic table, we'll talk about why hydrogen is that way. But what I want to really stress tonight is, I'm sorry, I'm recording this at night. You may be looking at it at 2 in the morning. What I want to stress tonight is how incredibly empty atoms are. It is hard for us to imagine that everything around us is made of atoms, but those atoms are 99.999% empty. And we'll talk about what that means. So let's imagine this. If I had a small, marble, and I said, I'm going to blow up the proton that is in the nucleus of hydrogen. Now, hydrogen only has a proton. It doesn't have a neutron. It has one proton. If I was going to enlarge that proton to the size of my little marble, and I went to any professional football stadium in the US or soccer stadium in other parts of the world. And I place that marble in the very center of the field. And then I looked for the electron cloud. Now, it's hard to describe the size of an electron. It's roughly said that an electron is 1/1000th the size, 1/1000 the size of a proton. My real physicists are going to argue with me on that, but that's kind of a rough estimate. So you're talking about, we've got this marble and we've got something that maybe 1/1, to divide that into 1,000 pieces, 1,000 tiny little pieces. That electron exists somewhere in the stadium. Not just on the field, somewhere in the stadium. So we can model the entire hydrogen atom, the electron cloud, the area that the electron exists in is as big as a professional football stadium that can seat 100,000 people. And the nucleus is a marble sitting on the 50-yard line. All the rest of that is basically empty space. Now, there are arguments that the electron is actually occupying all that space. We'll talk later about quantum mechanics, because there's this really weird thing in quantum mechanics that says you can't know the location and the speed and the nature of any particle in the universe exactly, all three at the same time. So if you go to find the electron, you'll find it somewhere in that space. But if you're not looking for it, it's everywhere in that space, basically all at the same time. I know it sounds complicated, but it's a detail you don't need to worry about unless you're going to be doing quantum mechanics, quantum physics. We're not really going to do that. We'll touch on it because it's interesting, but just understand that these atoms are basically very, very empty. In fact, one of the activities I used to do with my students is we did a scale model of the solar system where we would blow up the sun to roughly the size of a marble, of a large marble, one of the shooters, I guess. And we would put the solar system out on a football field, a soccer field, 100 meters, for the orbit of Neptune. And then we would go out and we would pace off. We would put a little stick with a little ball on it down for the sun, and then we would have little sticks with little round circles on them for each of the planets as we moved out. And we'd get all the way out to Neptune, and we'd look back. We couldn't see anything because that little ball's not glowing. If it was night and the ball was glowing, you'd see the light. But in the daytime, little black ball down there, you can't see it. Well, if you do the atom on the same scale, if you do the hydrogen atom to that same scale, make the hydrogen atom the size of that sun, that big marble, the electron is somewhere 300 meters in any possible direction from that, 3 times farther out than the orbit of Neptune. So the atom actually has more empty space in it than the solar system does. And to me, when I first learned that, it was mind-boggling. Because we see things as solid. But in reality, all the solidness is simply atoms that are linked together with electron clouds. So why can't I push my hands through each other? Why do I feel things that are solid? My students always kind of like this one. And again, for you physics nerds, don't come at me. I'm trying to make this understandable. The electron clouds surrounding the atoms that make up the surface of my hands are negatively charged. And when I go to push them towards each other, as they get towards each other, the force of the negative charges repelling each other gets greater and greater and greater the closer they get together. And it increases in a way what we call exponentially. So when I half the distance, the force doesn't double, it quadruples, it gets 4 times bigger. And when I half that distance, now it's going to be 16 times bigger. And I half that distance, and now it's going to be, what's 16 times 16? Or 4 times 16. It just goes off the chart. So the closer I get, the more there's repulsion between those electrons, and that's what we do when we say I'm touching something. The electrons in the outer surface of one hand are repelling the electrons of the outer surface of the other hand, and that force is very, very strong when we get the electrons close enough together. We can't get them touching. They don't touch. They just repel each other. So I used to joke when I taught high school, I said, next time you're caught in the hallway holding hands with your girlfriend and the principal says, y'all need to quit touching each other, you say, I'm not touching. The electrons in the outer surface of my hand are simply repelling the electrons in the outer surface of her hand. We are not touching at all. I don't know if any students ever tried that or how much trouble they got into, but technically they're correct. Nothing ever really touches anything else. It's just the electrons in the outer surface repelling the electrons in other outer surfaces. So that's all for tonight. Next week we will pick up taking what we've learned about the atom and how that relates to the periodic table, and then how that relates to how things stick together to make big solid objects like me and you. It's been fun having you here tonight. And as I always say, once you know, you know. Have a good evening.